and let's get started. So today we're going to talk about network models, and we'll start with the first network model, a random graph. Okay. So last time we discussed that there are several empirical network features that we see in real graphs. Those include power law, heavy tail, degree distribution, small average distance or graph diameter, the existence of large clustering coefficient, which is the transitivity, the fact that if you have two nodes, that the probability that they're connected is pretty high, and there is a gigantic connected component that exists in the network. So we're going to talk about a few models that will allow us to sort of predict network features, network behavior. They're models, and being a model, it means trying to have a simplifying view of the world, which means they will sort of describe certain features, but will be far from perfect. So there are several models out there. Well, actually, there are a lot of models today that tries to describe networks, but there are several sort of basic models. Everything else is somewhat derived from them. The very first model is actually a random graph model that was proposed by Erdos-Reni in 1959. It was a long time before anybody thought of social networks as well as social networks. It was a mathematical model, but it's really, really beautiful model and solvable model. So a lot of properties can be calculated really well. In fact, back until late 90s, until the discovery by Barbach and Albert that the web graph does not follow doesn't follow Poisson distribution, the distribution of node degrees. People believe that it is a sort of classical random graph model. And later on, when it was discovered that it is not, people start working on other models. And so you see that sort of the first reference is a random graph model 1959, and the next one is a small world, which is 1998, and preferential attachment 1999. And if I started following the references, it'll be probably 20, 30, 50 more references since then on various models. Right. So today we're going to talk more about the model, and and we start with a random graph model by Erdos-Reni. Okay. So what is a random graph model? So the mathematical formulation is the following. Let's say I have a graph G. The graph has n edges. N nodes and m edges, and the notation will be the nodes are the set P, edges it's set E, and those are the sizes of the sets. Let me try to get a notation working. Okay, so there are two models one can think of. One is so-called GMNM model. So the idea is you want to try to build a random graph with n nodes and m edges. And the way this is done is you select one of all possible graphs with m edges and n nodes. Now, if you have n nodes, the total possible number of connections between them will be the total number of pairs you can make out of n nodes. And that's n times n minus 1 over 2, right? That's the total number of pairs you could make. So the idea is that out of those pairs, that's the maximum number of edges you can have in a graph. We select m edges, And we select, when we select m edges out of that number of edges, that's how many combinations of m edges you can select, right? So then from m choice n. And you consider a random graph to be one of those configurations. So the idea is you generate all the possible random graphs, and then you just, all the possible graphs with m edges and n nodes, and randomly select one. And we call that a random graph. So in this model, it's very clear what m is. The graph that is selected has n nodes and m edges, and it is random in this sense. But this model, this definition, is not very constructive in the sense. In order to build it, you actually need to create all those graphs and then randomly select one. Another approach, much more constructive approach, is a so-called GNP model. In this case, what's given is a number of nodes and the probability that each pair of nodes out of the given nodes is connected. So pretty much it means the following. So you have a bunch of nodes. And then you go over all the pairs of nodes, and there is a fixed probability P. And you go over all the pairs of nodes and connect them with this probability. In other words, if you're actually building this, what you do is for every pair of nodes, you flip a coin, and you can compare the probabilities, and you create a random number generator from 0 and 1. And if the probability that you generate is less than P, you do not connect them. If it's greater than P, then connect them. And so such a way you build a graph. And it's clear that if P is getting higher, then there are more and more edges will be in this graph, and it'll become more and more connected. So that's called GNP model. In this model, m number of edges in the graph will be a random number, which means every time you run this again, you'll get different m, because what's given to you is this probability P that nodes connected. So since m is a random number, what you can do is you can calculate the expectation value or average of m. Well, it's obvious what it is equal to. It's the probability that two nodes are connected times the total number of the maximum number of possible pairs, right? The total number of pairs is n minus 1 over 2 times the probability that they're connected gives you the expectation value for m. You can also calculate, since again we are connecting this edges randomly, the node degrees themselves will also be will also have different values depending on the run, depending on the iterations you do. And so you can also calculate the average for the degree distribution. Well, the average for the degree distribution is, of course, 1 over n, where n is the number of nodes, sum over all node degrees. And it is equal actually to twice the number of edges divided by the number of nodes. Do you guys know why this is equal to 2m? Have you seen that before?
No.
No. All right. Let's look at this just for fun. Okay. Let's say we have a graph, 2 nodes. This graph, 2 nodes. All right. The node degree is 1. Node degree is 1. Sum of 2 node degrees is 2. We have 1 edge. So the sum of the node degrees equal to twice number of edges. Here's another example. Let's have this graph. Okay, every node degree is 2. All 3 together 6 divided by 2 gives us 3 edges, right? Okay, well, this is a proof by example. Of course, you can actually calculate this, But the idea is that the sum of the node degrees in a graph is always equal to twice the number of edges. And the reason for that is very simple, because every node degree actually contributes to the edge, right? And if you can think about nodes as a sort of node with a stubs, and the stubs is sort of degrees of the node, then when you create a graph, you connect those stubs. And so every degree contributes sort of 1/2 of a stub. And so the total sum of all degrees will be twice the number of edges. Okay, so because of that, we take this sum of the node degrees, and we estimated that the number of edges is m, so to 2 over n. We can substitute from here the value for m. It becomes p times n minus 1. And since n is pretty large, it becomes an average p times n. Okay, now this is actually a very, very important formula. We're going to be using it all the time. It really says that average node degree is equal to the probability, p, the probability in the model, times the number of nodes in the model. And these are the parameters. So remember, the graph is called GN.
Ну что, мы ждали проект? Да, представляете? На самом деле. Все, можно оставаться уходить. Интеграция сегодня.
All right, just a sec. I think we'll need to turn off the microphone for someone. Okay. So, all right. So this is K, right? And P times N. And so what this means is the following. When you increase P, the probability that two nodes are connected, you increase on average the average node degree in the graph. All right. This is an average, which means it can be less than 1. It can be like, for example, 0.1, or it can be 5, whatever, because it's an average number. It doesn't have to be an integer. But P literally tells you, P and N tells you how many on average every node has connections. And it's very clear. If K is small, so average number of connections is small, and if it is less than 1, then we most likely will have a lot of disconnected pieces, simply because it means on average node has less than 1 connection. We can also estimate from these numbers, we can also estimate sort of classical values of the graph density. And graph density is a number of edges divided by the maximum possible number of edges. Well, which is in this case is just the same raw. Okay, so the same P. So you can think of this P as a parameter as the density of the graph. So is G and P model, what's given is a number of nodes and the density of the graph you're trying to generate. Now, Erdos-Reni showed that in the limit of large n's, these two models pretty much becomes the same model. And so we can use either of them. We're going to be using, in our lecture, we're going to be using the GNP model. So we're going to be working with GNP model. Okay. Okay. So the question we would like to be able to answer is is actually within this model, what is the probability that a particular node has a degree K? So what we want to do is we want to find out the distribution, degree distribution. probability that the node I has degree k or P of k. And we've seen before that in power degree networks, in power law networks, that was a power law. Let's try to understand this distribution for random graph. The idea is the following. This is really sort of Bernoulli trials. What you have, if you remember, the Bernoulli trials is a situation when, for example, you're shooting the target and there is a probability that you hit the target, and then you have 10 shots, and the question, if your probability to hit the target on a single shot is 1/3, and you're firing 10 shots, what's the probability that you hit the target 7 times? Okay, so it's exactly the same idea. We have a node, and we're trying to calculate the probability in this random process that the node has k neighbors. Okay, node has a neighbor if it is connected to this neighbor, right? And probability for a connection is p. So if we're wanting for a node to have k neighbors, the probability of that event will be p to the power k. But at the same time, it shouldn't be connected to the rest of the guys. So if p is a probability that is connected, then the probability that it is not connected is 1 minus p, and it shouldn't be connected to the rest of the nodes. And finally, the question is, since there are that many nodes around, and the node is connected only to k of them, well, we should be able to select those k nodes out of the total number of nodes. And that given by this c k choose out of n minus 1. It is out of n minus 1 because, well, one node is this node itself. So we're left with n minus 1 to choose from. Okay, make sense? Okay, so this is classical Bernoulli distribution, and that the probability that the randomly selected node has from the random network has a degree k. Okay, now if we actually take this p of k and fix the average degree of the node, and as we've seen from the previous slide, average node degree is actually p of n. Yeah, we'll just call it lambda, and take n going to infinity, which means we'll be building a huge graph. Then the distribution will become a Poisson distribution. Okay. So you probably have seen this trick how to go from Bernoulli to Poisson in a course of the probability theory. If you have not, I would recommend you to actually try to do this. You can actually go from this formula to this in the limit of n goes to infinity, using the ideas from, take this c, write it down through this factorials, express factorials through Stirling's formula, and at the limit of large n, you can actually get this. Okay, that's it's a good exercise to do. Okay, so what does it tell us? Well, it tells us, first of all, that the random graph is not a power law graph. It's actually, has Poisson distribution, so it's a Poisson type of graph. And in some sense, we could have stopped here because, well, we want to model networks that occur, that we study, and it's clear that the distribution is not just the right one, okay? But at the same time, this model is actually one of the few sort of solvable models where you can totally predict the behavior of the model and features, and actually possess some very, very, very interesting behaviors for different values of the model. So it's still worth studying. In particular, the interesting part is in the following. You can use this model as what's so-called in machine learning a null model or null hypothesis, which is you'll be able to compare the real graphs, the real world graphs against this model. So there's something to compare against. And then you'll be able to make conclusions whether the graphs that you see are actually randomized or so how they're different from being random. Okay, so what does this random graph model look like? Well, this is sort of classical Poisson distribution. Nothing new here. Just again, a reminder that when we were dealing with power law distribution, we were expecting something. Well, okay, that's a bad picture. We would expect something to decay, and would expect something to decay really, really sort of quickly like that. Or I can try to draw it again. I need to learn to draw on this thing. Okay, all right, that would be, for example, power law distribution. Poisson distribution is very different. Poisson distribution has a maximas. You can clearly see it right here and right here. So which means it has probable node degree. I'm sorry, the node degree is a maximal probability, right? And that means that majority of the nodes have a degree around sort of this, around, for example, for this parameter is around 10. And there are some nodes with a less degree, there are some nodes with a higher degree, which means that most of the nodes have 10 neighbors, 10 friends in this model. Some nodes have less than 10, some nodes have them more than 10, but not very far away from that. It's very, very different from the distribution, the power law distribution. If you look at this formula, you can easily see that the maximum of the formula happens when k equal to lambda, right? Okay, so now we know the p from k, and let's look a little more at the properties of the random graph. So just let's think about this. When we're looking at G and P as a function of N and P, two parameters. Let's for a second fix N. So let's say we have 10 nodes, 100 nodes, or whatever number of nodes. And when P is equal to 0, they are just separate nodes. When P is equal to 1, that means in the process of a construction, we go through all the pairs and we connect all of them, because the probability that the two nodes are connected is equal to 1. Well, this means, I'll try to draw it. It's going to look like a mess, but this is a totally connected graph, right? Every node connected with every other node. So somehow, somewhere, going from disconnected nodes, we're getting to a totally connected graph. Means somewhere on the way, there should be a situation where, for example, those nodes for the first time become connected, right? So there must be some sort of transition period when you go from low degree P, from P0 to P1, where there is a connection happens, where all the nodes become connected. And so which means there should be a critical P when the structural changes start happening. In fact, the structural change is a phase transition. It's something maybe you remember from physics. For example, when water is freezing, the temperature is dropping, and then at some moment you get an ice, right? And the phase of the substance changes from liquid becomes solid. Well, the same way is here. There are disconnected nodes, and we're changing the probability, and so we start getting a few edges here and there. But then there's some moment happens when you get all of a sudden large component when things getting connected. And then when you increase P, every node becomes connected. So this critical moment when we're getting gigantic connected component. And it, of course, exists after the critical value of P. So before critical value of P, we have a bunch of separate nodes. And when critical value of P occurs, nodes becoming connected. So here's the picture.
May I ask a question?
Do you guys have a question?
Yes, I have a question.
Yes.
Why this critical value? No, it seems obvious, but I don't understand why this critical value is only one.
Oh, why there is only one phase transition and not anymore?
Yes. It seems kind of obvious that it's some monotonous, something monotonous, but maybe you can give more strict explanation on this fact.
Okay, yes. So what we're going to do is we're actually going to derive, we're going to calculate the point when this phase transition happens. And so you will see why it happens only once. But intuitively, the idea is the following. If you look at these pictures, you will see that when P is less than critical, right, we have say, for example, we have, piece here that is connected, there is some nodes here connected, there is something connection here, some connection there. Then when we're getting closer to critical value, they start connecting. Now, exactly at the critical value, well, I need to actually go a little bit above to see all of them connected. But think about this. We consider this phase transition when all the node becomes connected, right? And when this happens, it's still before the moment we get cycles. And so if you remember, you can think about this as a minimal spanning tree. Do you guys know what minimal spanning tree is? Right, so it's the tree with the smallest number of edges that connects all the points, with the tree with the smallest number of weights on the edges. So in some sense, it's a unique moment when things get all connected, so you can get from every node to any other node. And that's sort of a single moment. There is no other phase transition like that. After that, what's going to be happening is you start getting cycles in the graph, and things get denser and denser and denser. But the moment when, for the first time, all the nodes becomes connected, so you can get from one node to any other node in the graph, it just happens once. And in a sense, that's the idea why there is only one point for this phase transition. But we'll derive the equation on the next slide. So on this picture, you actually see sort of three stages. One stage when we have very low density, one stage when we're close to the critical density, and one stage when we're above critical density. And what I want to point out is here, at the critical value, though not all the nodes connected yet, but they will be very, very soon, you pretty much see the tree, well, and there is one cycle in here. When you're going further above the critical value, you can see a lot of cycles here and much more complex structure. Okay? Any questions about this?
Is this number depends on n?
Say it again, I'm sorry.
Is P and C depends on n?
So PC is a critical value, right? And we will actually find the critical value, and it does depend on n, on the number of nodes in the graph. Yes. Okay. This is weird. Okay, so here if I just increase even more density, and you see that the graph really becomes dense, and well, you cannot say anything here anymore, right? But that's what happens when you start densifying, and if you increase p to the point where p is equal to 1, well, you'll get a complete graph. Okay, so let's try to logic and determine this phase transition. Now, this is not this is in some sense it's not a proof that Erdos-Reni has it in their papers. This is what's called mean field theory or mean field proof, where we're trying to prove things on average. So here how it works. Let's assume, let's call U a fraction of nodes that do not belong to a gigantic connected component. Now, that thing where all the nodes are connected is called, of course, connected component, and because it's one and big, it's called gigantic connected component. So shortly, GCC. So we have this, GCC where nodes are connected between themselves, and we have a node here, and we're trying, and there is another node, and another node, and another node, and this can be connected to this node, but they do not belong, they're not part of this gigantic component with the rest of the nodes, okay? And so what we're going to try to do is we try to figure out when these nodes join the gigantic connected component, and when the sort of component grow to cover all the nodes in the graph. And so the graph will become connected. So if U is a fraction of nodes that do not belong to GCC, so the number of nodes that do not belong to this graph, then how can this happen? Well, the node that does not belong to the gigantic component can still have neighbors. But the trick would be that if the node does not belong to gigantic component, its neighbors should not belong to the gigantic component either. So it can be connected to other nodes, but those nodes should not be part of the gigantic connected component. And so then, on average, the fraction of the nodes, or the probability that a node does not belong to a gigantic connected component, can be calculated as the following sum. It should be equal to the following sum. Well, first of all, if the node, say we're looking at this node, if the node is connected to some other node, which means the node degree is equal to 1, then that node should not belong to gigantic connected component. Or our node can have two neighbors if the node degree is 2. Well, each of them should not belong to the gigantic connected component. Or the node can have 3 neighbors. Well, each of them shouldn't belong to the GCC, and etc. And so in mean field understanding of things, that statement should be true, right? So U should be equal to this total sum. Again, this is a fraction of the nodes, or probability that the node does not belong to GCC, and because it still can be connected to other nodes, it can be expressed in the following fashion. Well, then what we can do is we can actually use the Poisson distribution that we already calculated for a random graph and substitute it here. So this is pretty much the sum. It's this expression just written as a sum. And if instead of P of K, I substitute Poisson, that's what I get. But now you can easily see that you can take U of K and combine it with lambda. All right. By doing so, we take e to the minus lambda power, pull it out of the sum, and what remains within the summation is just exponent with lambda u. This is a Taylor expansion for an exponent. And you multiply them through, you get this. Okay? So what we did is we actually created a so-called mean field equation for the parameter u. Okay. So it is u equal to e to the power lambda u minus 1. And the solution of this equation, u, is a fraction of the nodes that do not belong to a gigantic connected component. And just to remind you that lambda is what we also called k average node degree is p times n. So lambda actually contains the parameters of the model, contains probability and contains n. Okay, so now we have an equation. Well, it's not a very easy equation to solve. We have u, and here we have exponent with u. The way to do it is, here we're going to play a little trick to actually solve this equation. First of all, we're going to change notations, and we do it just for the convenience. Now we call S fraction of the nodes that do belong to a gigantic connected component. So U was a fraction that does not. S will be a fraction that does. So if S is equal to 1, then every node in the graph belongs to GCC. Okay? So S is 1 minus U. We just take this and substitute in the equation. We get the following equation. Okay, let's see that this equation makes sense. What happens when lambda becomes very large? Lambda very large, so lambda goes to infinity. Lambda is p times n, which really means for lambda to go to infinity means we need to increase the density. So what we're trying to do is, let's take a graph and start increasing the density such a way, and increasing density and n, the size and the density, such a way that lambda will go to infinity. Well, if lambda is very large, what happens to the right side? What happens to this term if lambda is very large? Yeah, S cannot be negative. S is a fraction, so it goes to 0. So the solution of this equation, S equal to 1. Well, it makes sense, because when we have large lambdas, it means very high density. It means, yes, we should eventually get every node belonging to the component. So S is a fraction of nodes belonging to the component. When lambda goes to 0, on the other hand, lambda goes to 0, that really means that we're dropping P to be very low, so the density is very low. Let's look at this guy. What's going to be happening then? Well, if lambda goes to 0, this becomes 1. So, and the only solution here is S equal to 0. So, I mean, the equation makes sense. The only question is how to solve this. Okay. What do you guys think? How can we solve this equation? I'm sure. Yeah, go ahead.
You can solve this numerically.
I cannot hear you, unfortunately. All right. Let me show how to do it. Let me show you how to do this, and we'll think about how to deal with microphones for the next lecture. So the idea here is the following. We sort of do graphical solution on this thing. Let's look at it. So that's our equation. The only thing I have done is I moved e to the minus ls on the right-hand side. Let's look at this guy and at this. Let's draw them. So here, I'm gonna draw two functions. I'm gonna draw functions y equal s, and this is a straight line, right? Diagonal line. Now I'll draw a function y equal 1 minus e lambda s. So the solution of this equation is, well, I'll call it when, okay, y1 is equal to y2. Okay, so when those two lines intersect, that is a solution of our equation. Let's try to draw those curves for different values of lambda. And though here we have notation C, it's because I borrowed this picture. It is lambda. Notice that in this case, depending on lambda, the curve will either go pretty low or can go higher, right? That is controlled by the parameter. So if lambda is small, it's low. If lambda is large, it can be bent more. So let's see where this equation has solutions. So where those two curves intersect. Well, one point of intersection is obviously always at 0. So when s equal to 0, there is a solution there. Right? When s equal to 0, this is 0, this is 1, 1 minus 1 is 0, there's always a solution. But we are interested in a different solution. We're interested in a solution different from 0. And that solution will exist if these two curves intersect somewhere else, like right here. And the question is, can we come up with a condition when this non-zero solution exists? And the answer is yes, we can. If we look at this picture, you will see that the only time this condition, this non-zero solution will exist is when the curve, the second curve, this curve starts at the origin steeper than the horizontal line. So when this angle is greater than this angle. Because if it is, well, there will be an intersect. If it starts below, it will never intersect it. So the condition for the existence for the solution for this equation is the fact that this angle between the curve, is greater than the angle for our line. Well, how do we find that? Well, that the angle is a derivative. And we just need to take a derivative at origin and just see if it's greater than 1. Why 1? Well, because the derivative from this is 1, is diagonal line. So we take this expression and differentiate. The derivative from this is lambda e minus lambda s, and compare it at s equal to 0. Compare it with 1. And if it's greater than 1, there will be non-zero solution. If it's less, there is no non-zero solution. So the critical value, it's clear, will become when the tangent of the curve is equal to 1, where it just touches our horizontal line. And that will be the critical point. Okay? Substituting here 0, it's clear, you can clearly see that lambda is greater than 1, we'll have a non-zero solution. So the critical point is when lambda is equal to 1. And just sort of unwinding back, lambda is really nothing more than average node degree, which is p times n. And the condition for the critical point is actually p critical is 1 over n. Like you ask if it depends on n, yes, it does. And here is the condition. So pretty much what it says is the following. If a node, on average, has more than one neighbor, it belongs, there is a gigantic connected component, and they're all connected. If it has an average less than one neighbor, they are disconnected, which sort of makes sense. If we try to draw here the size of the connected component, and the size of the connected component is actually this solution, so it's this value. This would be the size of the connected component. Let me try to undo this. Okay, I cannot undo it, just one. All right, this will be the size of the connected component. So this is the size, this is the size. When, when we just go above the horizontal line, we'll have a small connected component. Then it gets bigger, then it gets bigger, gets bigger, so the solution becomes larger. So we can plot the size of the connected component as a solution of this equation as a function of average degree. And you see that the size of the gigantic connected component is equal to 0. So it doesn't exist until we reach critical value. Critical value is the mean degree. So mean on average degree becomes 1. And then all the nodes start belonging to the gigantic connected component. And on this side, we have this sort of hairball. Here we have separated pieces of the graph. Sorry. So that is sort of the essence of the phase transition and the essence of random graph model. Any questions on this slide? Okay, let me do this. Since I cannot hear you, but I can see you, please raise your hands if you understood this. Great, at least I know that we're not asleep. Okay. Okay, thank you. Good. Are we moving too slow? Shall we go faster?
Yes.
No? Yes?
Yes. Yes.
Okay. So move quicker. All right. Okay, so here is, so previous picture was really just sort of numerical simulation solution of the equation. Here, I'm sorry, solution of the equation. Here, it's actually a simulation on the graph model itself. When I took a simple model, just generated a random graph. In this case, it's, what was it, 100,000 nodes. I took 100,000 nodes and was changing p, looking at different values of p, and calculated the size of gigantic connected component. And you see, until I hit on average k equal to 1, the size was pretty much 0, and then it started growing. So the theory predicts the experiment very, very, very nicely. And that's why everybody loves this model. And here's an example when we're at 4, where average node degree is equal to 4. Here, the distribution of the node degrees of the graph. So again, you can see the average here is well 4, and that's terrible. Okay. The average here is around 4, but there are nodes with lower degrees in the graph, right? And the nodes with higher degrees in the graph. But this is a Poisson random graph. This is a Poisson distribution. Okay, and it corresponds to this particular graph corresponds to like this data point. So when k is equal on average to 4, means all the nodes belong to a gigantic connected component. So, okay, so what happens? Just sort of to reiterate, when we take the graph to n go to infinity, the critical value for the phase transition is 1 over n. When p is less than critical, which means on average, every node has 1 neighbor, there is no components that have more than O, capital big O from log n nodes. So it's a logarithmic number of nodes in a component. We haven't shown that, but this can be calculated, and it was done by Erdos-Reni. When we hit the critical point, k equal to 1, we get the largest component of this order of magnitude. Like n to the power 2/3 of all the nodes will belong to the largest component at that point. And when p is greater than critical, which means on average every node has more than one component, pretty much every component will be in gigantic connected component. So that's what we saw. And here are the really pretty picture generated by Aaron Closet. I borrowed it from his slides. So what's shown here is the following. On the vertical axis here, we have average node degree. So this is average k, right? So this is average k is 0.5. This is 1, which is critical. This is a critical point, critical value. This is on average every node has two neighbors, has 4 neighbors. And on x-axis, this is just the size of the graph. And if you notice here, for example, you can see the connections. And what happens is when you increase the size of the graph, and if the density of the graph or average number of nodes is, average number of connections per node, average degree is low, what's happening is you have a bunch of these disconnected pieces. When you hit the critical point, well, they start getting connected into those trees. There are all of them, almost all of them trees. When we increase the density of the graph, we start getting loops, cycles, and when the density is very high, well, you get the sort of hairball where things are very, very much connected. So guys, question for you. Based on the theory and the phase transition point, we actually should have things connected, because that's when we get gigantic connected component. And if you remember, the theory says, what was that? 2/3, right, of the nodes. Well, it doesn't look here like 2/3 of the nodes belong to the gigantic connected component, or at least here. Where can we make a mistake? Where was wrong? Well, honestly, we didn't make a mistake. It's just the fact that when we look at the theory, remember the theory was looking into this limit, right? And we never at this limit. So if n becomes larger and larger and larger, we will see that it is 2/3 of the points belong to the gigantic connected component in the phase transition. But when n is small, and typically when you make experiments, n is relatively small, you might see a bunch of disconnected nodes still at critical point. In fact, again, this is a random graph, which means when you repeat your experiments, you might have quite different pictures in every iteration. And these things are valid on average, right? Remember, we were talking about average, okay? But this is what you can expect from the random graph models. Again, this is a very interesting mathematical tool in the sense that you can explore things and you predict things for this model that you really cannot predict for other models, not even close. Okay. So there are actually even more cooler facts you can calculate for this model. For example, you can actually calculate and you can predict when in the random graph you start seeing trees, when you start seeing cycles, and when you start seeing, for example, complete subgraphs. At which values of p they first appear. So what's shown on this picture is the following. We are actually increasing P from left to right. And there are a bunch of sort of microcritical values that are this one. So there's a threshold probabilities for appearance of subgraphs of K nodes and L edges in the random graph. Well, I'll give you an example. If we have a tree is a subgraph that it is minimally connected, and which means if you have n nodes, a tree should have, K nodes, a tree should have K-1 edges. Otherwise, it will not be a tree. There will be a loop. So there is a critical point, the critical value of the density when trees with K nodes start appearing. Like, for example, if there is a tree with, say, 4 nodes, then the critical value will be -4 divided by 3. So it is right here. That's the critical value. So when P is getting greater than this value, we start seeing this type of trees in the graph. When P is getting to be n-1, so P proportional to 1 over n, then we start seeing cycles. And in fact, this is a point where the phase transition happens. So when the phase transition happens, we start seeing first cycles in the graph. And if you can start increasing P, you can, for example, get to the point where you start seeing complete subgraphs. So again and again and again, this model that is fully controllable in the sense you can actually predict lots and lots of very interesting events that happen in the graph. And the practical value of this is that you can compare the graphs that you have at hand with this model and see how far it is from like random graph, or what you could expect from the model if it was a random graph model. All right, so there are several other things that you can calculate, that we can calculate for this model. They're pretty easy to calculate. Well, we talked about clustering coefficient, right? Clustering coefficient is really is just a number of it's a number of closed triangles, right? So you have a node and you have neighbors. Then clustering coefficient will be just the ratio of those closed triangles to the total number of possible triangles, with one node belonging to the one we're trying to explore. Like, for example, or in other words, the definition would be it's a number of links between nearest neighbors. So here are the nearest neighbors. We have 1, 2, 3, 4, 5 of them. So it's a number of links between nearest neighbors divided by the maximum possible number of links between nearest neighbors. If we have K nearest neighbors, then the possible number of links between them will be K times K-1 over 2. It's again just number of pairs, how many pairs you can form out of K nodes. But the total number of links between them that exist in our model will be the maximum number of links times the probability of the links. So the clustering coefficient is actually equal to the parameter P. And it also makes sense simply because what we're saying is that the probability that since connection of every node is independent from connection between other nodes, then the clustering coefficient, which is a probability that two of your friends know each other, is actually just equal to P itself, the probability that two randomly selected nodes are connected. Well, it's good and bad. I mean, it's good because it's very easy to compute. It's bad because, well, we can actually, because of this, and if, for example, we have a fixed number of fixed node degree, fixed average node degree in the graph, when n goes to infinity, when the graph becomes larger, the clustering coefficient goes to 0. Why is it bad? Well, because in the real networks, it's not so. The real networks becomes bigger and bigger, and the clustering coefficient should not decrease. The ratio, the fraction of the triangles in the real network still remains very large. We talked about the large clustering coefficient for those networks. While in random network, clustering coefficient tends to go to 0. And that's sort of another reason why this model does not describe real network. Now, another way to think about this is you remember that for some smaller number of p's, random graph looks, almost like a tree. Now, when p goes larger, it doesn't look like a tree anymore, but it still does not have enough connections, enough small size loops of size 3, that are responsible for clustering coefficient. And when n goes to infinity, clustering coefficient tends to 0. When you have fixed k. On the other hand, because of that property, we can easily calculate the diameter for this graph. Since again, clustering coefficient is very small, which means there are very few triangles. Again, as an approximation, we can think of the graph as being almost a tree, or at least locally like a tree. And then you can easily calculate how many nodes on average live these steps away from the current node. Again, this is just a very, very rude approximation, but still, if a node has a degree, if the average degree of the node in the graph is k, then it has k neighbors, and each of those neighbors on average will have k other neighbors, and again, it's on average, so some will have more, some will have less. And so after d levels, d steps will cover approximately average k to the power d nodes will belong to this graph. Well, then you can equate this and take log from both sides, you will get this property. Now, again, if we take a graph and we'll fix the average node degree in the graph, the diameter of the graph, or average shortest path, will behave cog logarithm of the number of nodes. Now, what did we call this property? We talked about it last time. Small world, yep. So this is really what it says, that this model, though it does behave badly in terms of distribution, well, not badly, it's different from real world networks in terms of their distribution and clustering coefficient. It does express the small world property, which means that on average, the distance between nodes behaves like logarithm of the number of nodes. So it shows the small world property. So you need very few hopes to jump from one node to another. Okay. So graph diameter is pretty small for this network. Okay, so these are the three main properties we're going to be looking at in the model. So we're going to be looking at the degree distribution. We're going to be looking at clustering coefficients, and we'll be looking at average shortest path, or diameter of the network. And in the case of random graphs, we realize that the clustering coefficient is off. It's small, while in the real world it's not. The graph diameter, or average shortest path, is actually behaving correctly according to real world. And the node degree distribution is also way off, because in the real world it's power law degree, and what we have is Poisson. So the question is, well, are those models like sort of useless in this sense? And in fact, what we could do is we can actually adjust the model a little bit and fix at least the issue with degree distribution. And this fix has a name. In fact, it's called a configuration model. So the idea is the following. we still will be building a random graph. But this will be not just sort of your typical random graph, not like Erdos-Reni random graph, but it will be a random graph with a given degree sequence. So the idea is the following. We'll have n nodes, we'll assign n nodes, and we'll provide degree sequence for those nodes. So we'll literally say, okay, the first node will have degree 1, the second node will have degree 5, the fourth node will have degree 15, etc., etc., etc. So we'll just forcefully say what would be the node degrees. If we do so, we also need to, well, if we do so, we implicitly assign the number of edges, simply because you remember that the number of edges is related to the total node degree, the sum of all node degrees in the graph. And by doing so, we're building something like this G and M model, where we selecting n, and by providing degree sequence, we're selecting m. And then what we're going to try to do, we're going to construct a graph out of those by randomly matching the nodes such a way that we're going to satisfy those degrees. Well, which means really, okay, here are those nodes, and these are sort of edge stubs, which means like not full edges, but if node has a degree, say 1, 2, 3, 4, 5, well, we use this sort of stub with the 5 sort of stubs here. And so what we're going to do as a random process, we're going to just take any stub from here and connect to any stub from other node. Take this, connect to this. Take this, connect to this. Take this, connect to, I don't know, here. Take this, connect to this. Take this, connect to this guy. Take this, connect to this guy, etc., etc., etc. So the question for you, do you think it's always possible to build a graph this way?
No.
No, why not?
Because
we can have uneven number of stubs.
Well, let's say we did a good job and we actually guaranteed that the sum of all the node degrees will be equal to m. So it should be possible on average. But you're right in the sense that this condition will guarantee that we can match all the pairs. Like, for example, here, if I look at this picture, what's left? I think there is this pair, right? We can match to each other. We can match these guys. Do we have anything else left? Yeah, and there is this guy goes here. So what happened now, we built the graph, but in order to do that, since we connected things randomly, we actually created here and here, we created loops on the nodes. And there might be multiple edges between between the same two nodes. So in this process, if I actually give a sequence of node degrees and guarantee that I will try to build the m edges that is equal to the sum of the node degrees, I can build a graph. It's guaranteed, but this graph might contain self loops and might contain multiple edges between the nodes. In order for this graph to be simple, and simple means there is no self loops and multiple edges, we should have a very special graphical degree sequence. That cannot be just sort of random sequence. And there is a theorem actually exists how to build those sequences if needed. We're not concerned too much about this by the following reason. First of all, even if we build just sort of graph without following this sequence, the probability of having self loops and multiple edges will be quite small. And the other reason, we'll be actually taking this graph degree sequence from real graphs, those that already do not have loops and multiple edges, and we'll be using the graph degree sequence to sort of seed the random graph. We'll see it on the next slide. But before we go there, one more point is, so this is sort of, this graph is different from Erdos-Reni model. In Erdos-Reni model, probability P is a probability that any two nodes are connected. So here, the probability that two nodes are connected, the nodes I and J are connected, will actually depend on the node degree of the node I and J. And it's sort of obvious by the construction, right? Because if we take one node and we want to connect it, say node I, and we're trying to connect it to node J, so node J gives kj stubs in the world of sort of edges. But overall, there will be that many places you can connect to. So the probability to connect to this particular node is kg, so how many stubs it provides versus the total number of stubs available there for the connection. And for node I, there are ki ways to connect to the node kj because the node I has ki stubs. And so the probability that two nodes are connected is actually ki times kj divided by 2m minus 1, which is, with large M, is just ki kj divided by 2m. And just remember this, this combination of ki kj divided by 2m, we'll meet it, we'll see it many more times. And the idea, again, this is the probability that two nodes are connected in this configuration models. It is different from just P in random graph, in Erdos-Reni random graph. So how do we use this model? Well, here's how it's used. We can take a graph, like real world graph, and here is sort of one famous karate club graph, and actually using network X, it's built in, you can actually load it and play with it. And so this is a graph of the, created by sociologists. There was a karate club, and it was a bunch of students and several instructors, and at some moment instructors split into two groups. And before that, the sociologist went into the club and sort of talked to people, and based on their discussion, they created a network, sort of friendship network in karate club, and they later on could predict how the club will split. So who of the students will stay with one instructor and who will go with the other instructor. And so that's sort of the picture here, right? This is like one part of the club. That's another part of the club. And we'll talk about this when we start talking about clustering of the networks and communities. But at this moment, we just look at it for a different reason. This is an actual network, and there is no self loops, and there is no multiple edges. So the node degrees here are actually, create the right graphical sequence in this sense. So we can take this graph, we can take node degrees from this graph and seed it into a configuration model. And we'll create the model with the same node degrees. This is a random model. And so what it tells us is the following. This model has the same number of edges as, this model has the same number of nodes as Karate Club. This model has the same number of edges as Karate Club. And this model has the same degree distribution as a Karate Club because we took all the nodes from there. So the differences in the structure is pure to the fact that the model on the right is a random model, on the left has sort of some underlying process that was used to create it. And comparing to configuration model can help us to emphasize the impact of whatever underlying process was that was used to create the graph, compare to the random graph. So in some sense, we eliminate the effect of different degree distributions, and just what remains is the effect of randomness on the structure. Okay, so and that's why this is called a null model. And we can, for example, if we want to look for communities, we can say, okay, well, let's compare structure of this graph versus structure of the random graph. The random graph does not have communities. Things are connected at random. this graph has a communities. Well, how do we know that? We'll compare the structure to the random configuration. And one can show, I don't have a slide on this, but one can show that in configuration model, though the power law so configuration model, you can build any distribution you want. And if your original graph has a power law distribution, configuration model will have power law distribution. And it has also small world behavior. But one thing that it doesn't have clustering coefficient. The clustering coefficient for this model will also go to 0, which means that clustering coefficient is a very good symptom when you go from randomized structure to somehow ordered structure. In a randomized structure, there is typically no clustering, or clustering coefficient goes to 0. There is no triangles. And the fact that the graph has triangles, actually, it's a symptom that there is some other underlying process other than the random process has been used to create this graph. So that's pretty much it. That was sort of an introduction to random graphs. There are two sort of famous papers by Erdos-Reni. They are both available on our website. And if you're interested in this kind of stuff, go read them. They're not that difficult. Well, at least parts of them. And have been many more, much more work on the graphs, in particular on configuration model. There is a big chapter on configuration model and how you can compute with them in the book by Newman, the one that I also referred you to. So that's it for today. Any questions? Okay, so the slides will be available online. Andre, you here? Hello? Okay, well, he is probably not at this moment, but he should be back. And I think he's going to go and do his you guys or seminar also online today. So let's take a quick break, and then we'll start in 10 minutes. Okay.